So let's do this thing. Let's do this example. Example 3C, find the derivative. And I am given that u here is t plus t squared minus t cubed of that k, and v, the function valued vector is what I meant to say, is sine plus 2 cosine of t plus, ran out of room here, cosine of t. Okay, so those are our two function valued vectors. We are going to be asked to find the derivative with respect to t of u dot v. Okay, so let's do it right now. Excuse me. I have my derivative of the first, right, times the second plus the first times the derivative of the second. So the derivative here, I'm going to take the derivative of my first vector, which is u. So that's now going to be I plus 2tj minus 3t squared k dot the second, just exactly how it is, plus the first, exactly how it starts with, so t plus t squared plus t cubed dot the derivative of the second, giving me cosine minus 2 sine of t minus the sine of t. There it is. Remember, when you dot these, all you're doing is just multiplying, right? Because dot is scalar. So whenever I'm looking at these two vectors, so I start off with two vectors, and then the dot product is just a scalar value, so I no longer have i's, j's, and k's. I's, j's, and k's determine components of a vector. Well, I'm not creating another vector whenever I dot product these. We're just coming up with those scalar amounts, so I'm going to scoot this up a little bit. So now we just end up with sine of t plus 4t cosine of t minus 3t squared cosine of t plus t, oops, not sine, cosine, I don't know what I'm thinking, cosine of t minus 2t squared sine of t plus that t cubed sine of t. There it is. No more I, j's, and k's because we don't have a vector anymore. We just have this dot product, which is scalar. Okay, then you can clean this up a little bit. Oh, what do we have here? We have some sines that we can put together. We have some cosines that we can put together. Maybe I'll double line those. Okay. Let's do this thing. So now I have 1 minus 2t squared plus t cubed is the coefficient of sine. And then for cosine, I can put together this 4t and this t to be a 5t minus that 3t squared of cosine t. Honestly, you can put them together like that. I don't know what my math lab's going to have you do, but you can put them together like that. The big deal here is the fact that these are like terms, and you can put those together. Just however you want to pull that off. Cool. Taking the derivative, take the derivative of every single piece. That's it. Pretty nice, right? Check this. What if I want to do higher order derivatives? No sweat. You just take a derivative again. We want to compute the first, second, and third derivative of this vector. T squared, 8 natural logs of t, and 3e to the negative 2t. All right. So my first derivative is now going to be 2t and then 8 over t and then negative 6e to the negative 2t, right? Because you just chain that. And the second derivative is just the derivative of that. So 2. And then remember, that's the same thing as t to the negative 1. So you really end up with negative 8 t. And I'm just going to write this as t to the negative 2. You could put it in the denominator, leave it up there. I don't really care. And then I've got a positive 12e to the negative 2t because you have to chain that last one, right? The third derivative here of t, the derivative of a constant is 0. I have 16 t to the negative 3, and then bring that in front will give me that negative 24 e to the negative 2t. Just take the derivative of each piece. So the derivative of this vectored valued function, bring it, right? It's no big deal. Cool. If the derivative is no big deal, I bet you can guess that the integral also no big deal. Check this out. Definition: integrals of vectored valued functions. Given my vector is f of t, g of t, and h of t, the old standby, right? Such that f, g, and h are integrable. Oops. Integrable, yep. Then all antiderivatives for my vector have the form r of t dt, because remember t is my value that I'm looking at. If you take the derivative of each piece, lo and behold, you are also integrating each piece. To get that vector. Pretty sweet, right? In other words, if capital R of t is an antiderivative, because remember, vectors have many that we're looking at. So you can have infinitely many of the parallel vectors that you have, just changing the magnitude. So this is an antiderivative. Then my vector is equal to R plus C. Now, when you have this plus C, this C vector back here is a vector with constant components. Okay. So what this means is you're going to take the antiderivative of every single one of those pieces. So every single one of those components, I shouldn't say pieces, one of those components. And then every time you take this indefinite integral, you always have to add that plus c on it, right? Plus c every time. Well, every single one of those plus c's are put together to be this vectored with constant components. So the plus c all just goes together to be this one vector. So you just have to write it as this plus c at the end to account for all of those different pieces. Cool, let's do one. Not on this page. Let's do one over here. If I want to integrate t over the square root of t squared plus 2i plus e to the negative 3t j plus sine of 4t plus 1 k dt. So I'm going to integrate this with respect to t. Okay, we're just going to integrate every single part. So the first one that we're going to integrate here, it's going to be t over the square root of t squared plus 2 dt is going to be my first integration. Well, let's do a little u sub action, because remember, your go-to method anytime you want to differentiate, or pardon me, integrate, is u sub if at all possible. So this 1/2 du is now going to be the t dt, and I've got my sub out. So this is now going to be my integral here of my 1/2, I'm going to put that in front, of u to the negative 1/2 du. We take that antiderivative, I've got my 1/2, and I bring that in front, that's going to be times 2u to the 1/2 plus c. So this is really going to be the square root here of t squared plus 2, and then I've got plus c, that first plus c that we're looking at. That's all going to be, that c is all going to be combined into my vector value at the end, so it's just going to be a c there at the end. Then I'm going to integrate e to the negative 3t dt. So we've got that negative 1/3 e to the negative 3t plus c. There's my second piece. My third piece, I'm going to integrate the sine of 4t plus 1 dt. So that's going to be that negative 1/4 cosine of 4t plus t, and then my third c that we have. Sweet. So when we take this integral, we have every single one of these pieces that we put together. So my antiderivative of this whole thing is going to be the square root here of t squared plus 2i minus a 1/3 e to the negative 3tj plus this t minus 1/4 cosine of 4t, and I just put that cosine in the back instead, just so that I don't have this minus sign there. It just makes it a minus since that's a plus. That's the only reason why I did that. No other reason. Cleans it up a little, that's all. Okay, plus my c vector. And my c vector handles each one of these components. So that component gets lodged in there, and then that component, because it's just that vector value constant. I don't know what those constants are. It's just those constants that go together. And that's it. Truly, that's it. You take the derivative of each piece, you take the antiderivative of each piece. La! Pretty sweet, right? Cool, let's do one more. You can do an indefinite integral. We can also do a definite integral.